Welcome here. Today's speaker, Jonathan Sauder, will speak about 3D mapping of underwater environments. This is RISE Learning Machines seminars. RISE is Sweden's research institute with nearly 3,000 people working on a wide array of topics. Specifically, us at the computer science department work on applied AI projects for the benefit of society, and we organize these seminars every week. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. You can do that by dropping me an email, for example. Also, make sure to check out the collection of great talks on our YouTube channel. Today, I have the pleasure to introduce Jonathan Sauder. He's a PhD candidate in deep learning at the Environmental Computational Science and Earth Observation Laboratory at EPFL in Switzerland. His interests are in the intersection of optimization theory and signal processing with neural networks. And the topic today is unsupervised deep learning-based 3D mapping from video and its applications to underwater mapping. So with that said, I will hand over the word to you and stop my sharing.
Okay, just to double check one more time that everybody can hear me, just give me a thumbs up.
Yes.
Okay, great. So thank you very, very much for the invitation to speak here. So as it's been said, the title of my talk will be Deep Learning-Based 3D Mapping and its Applications in Underwater Mapping, and especially we focus on unsupervised methods. And yeah, I mean, you already kind of touched on it a little bit, but quick slide about me. So yeah, I'm a PhD student with a group at EPFL in Switzerland concerned with machine learning and remote sensing for environmental applications. But I'm also co-supervised by a second laboratory at EPFL that's more that has a focus on biological geochemistry, but also organizes expeditions for coral reef science. My background, as said, is computer science and machine learning. But in the context of this PhD, my project is to map the coral reefs of the Red Sea using machine learning techniques. And in this talk, we'll cover three main things. So the first thing is we'll briefly revisit conventional 3D mapping, so structure from motion photogrammetry. Kind of discuss when it works really well and when it maybe struggles. We'll talk about deep learning-based mapping, so this kind of learning-based structure from motion photogrammetry, and I'll go into the details of these figures. You'll see them throughout the talk quite a while, and kind of what problems these kind of learning-based techniques can solve, but also what challenges they introduce. And then in the very end, I'll go into a little bit of the applications of these kind of learning-based mapping systems, especially in the context of mapping coral reefs. So in conventional 3D mapping, there's a ton of literature. It's been around for quite a while. And from what I heard, I know that there's been 2 talks recently also in the seminar series concerned with 3D mapping. And just to make sure everybody can see the slides also, right?
Yes, no problem.
Okay, perfect. Sorry. And there's been 2 talks on this kind of structure from motion photogrammetry and its applications to augmented reality, but also from a more mathematical standpoint. And in general, there's 2 terms that kind of describe these set of techniques. I've used it a few times. Structure from motion photogrammetry kind of describes the notion where we have multiple camera viewpoints within a 3D scene from one or more cameras, and we want to find the underlying 3D geometry of the scene from this set of images from these cameras. And there's a very closely related set of techniques summarized under simultaneous localization and mapping, so SLAM. Usually SLAM describes the same kind of thing, but in a real-time context, so like a navigating robot or drone. And sometimes in SLAM, we include other kinds of sensors. like LiDAR measures or IMU measures. But within this talk, we'll stick to 3D mapping from visual input, so from images or from videos. And I'll use these two terms interchangeably, but we're really within the structure from motion kind of realm, because we're not going to focus too much on real-time applications. So let's start by kind of looking at state-of-the-art conventional approaches for 3D mapping. So state-of-the-art, it's okay. Well, modern structure from motion systems that use these conventional pipelines. And in conventional pipelines, the input, again, is like the set of images that we want to reconstruct the 3D geometry from. And the first step is usually extracting features from the input images. So these are points that are particularly salient, that are particularly interesting or rare, or something like edges or certain kind of features. The notion is a bit hard to describe in words, but it's points that can be recognized across images. And then these features are usually, we try to find the same features in multiple images. So this feature matching process. And these two really form the basis of all the other steps that come after. And just to kind of show an example. So when we have these two images, these are from the coral reef domain. You see the black little circles. These are the found features on each of the two images. And then the colorful lines are the images, are the features that have been matched between these two images. And it's usually a subset of the found features. In this one, it looks like they're also mostly correctly matched. But often there will be quite a few wrongly matched features. And this is usually detrimental to the performance in the end. So the rest of this whole pipeline is usually concerned with triangulating the features, it's like the distance from the cameras to each of these matched features from multiple frames, and then kind of iteratively updating both the camera pose and the depth of these features, and kind of removing outliers as we go. And if we run these kind of pipelines for long enough on large image collections, especially image collections with good quality and stable conditions, then usually we can expect an extremely good 3D reconstruction that's very precise. So we end up with this kind of sparse point cloud, and this can then be extended to a mesh or to a dense point cloud. And so the thing with these kind of pipelines is that in general, they work very, very well. So in a lot of other fields in computer vision, deep learning has kind of dethroned these kind of conventional vision systems for like almost 10 years now. In 3D reconstruction, it's not that clear. Even now, I would say that for many industrial applications, probably you're still going to be using these kind of conventional systems and nothing based on deep learning. So it's one of the later frontiers of the deep learning revolution in computer vision. However, there's also some kind of cases in which these classical methods really struggle. And I'm just going to show an example from the coral reef domain. And I think you'll be able to see why it's really challenging for these conventional methods. So here, we're filming over a reef in Jordan, in Aqaba. And you can see that the wave pattern, so the caustics, lead to this very noisy lighting behavior on top of everything we see. Furthermore, underwater, we have the problem that when we look at things that are far away, they usually are pretty blue or green if you have greenish water. And then you only recover the color of objects as you move closer. And then, okay, in this video, it's not so apparent, but sometimes you have quite some annoying, like for the sense of 3D mapping, objects like big fish or other snorkelers or divers. So you have moving objects. And these are usually very detrimental to the performance of these classical feature matching algorithms. And when you just naively apply these conventional structure from motion pipelines to this kind of uncurated, noisy video, with challenging conditions. Usually you have some wrongly matched features. I mean, here in this example, we don't have any wrongly matched features, but we only have features for the high texture regions and not so much for the flat sand. But there will commonly be one or two poses that are completely messed up. And then you often get these kind of gibberish reconstructions. So the reconstruction quite often fails completely with these kind of classical methods in the setting. And what I want to talk about today is can we use deep learning and especially deep learning based 3D mapping techniques that can deal with these kind of very noisy and challenging environments. And maybe there's a bit of a trade-off. We can lose some of the accuracy in the end. Maybe we don't get a perfectly centimeter precise point cloud, but we get something that works more reliably and works out of the box. And so one way to do this, which is being done in many domains, is basically just by supervised approaches. So in a lot of applications, you'll have a ground truth for training your 3D reconstruction system. For example, in the self-driving car domain or many other robotics domains, you can put a laser scanner on top of the same vehicle or the same robot that your cameras are on. And then from this laser scanner, you can get the actual distance. It's kind of hard to see on this image because it's sparse. You only get a sparse depth value for where the laser touches an object. But this can still be used to basically train a neural network to also predict the depth from this image. And then you get a dense depth prediction from from only the image. And technically you could remove the laser scanner, assuming that your depth prediction is good enough. And in a similar way, you can also put some very, very precise GPS instruments on a lot of robots that are usually accurate to a few centimeters. And then you can just predict how the camera moves, the camera trajectory also from just supervised ground truth labels. However, in a lot of scenarios, it's not really easy to get this kind of ground truth. A camera in general is very cheap, but a laser scanner and this sort of differential GPS is not cheap. And then, for example, in the underwater domain, it's not really practical to have underwater laser scanners. They don't really have a big range. They're very expensive. And the same for GPS. GPS doesn't really work underwater. You have to plant like buoys with a GPS and then use sonar to triangulate your position underwater. So you have a big setup for something that we hope could be done basically just from the images. And so this leads exactly to the set of methods that I'll focus on during this talk and that I focus on during my research. And these are unsupervised approaches for learning a 3D reconstruction. And the underlying method is actually, I find it very elegant. I find it very simple. Basically, we look at pairs of overlapping images. And we have a neural network that predicts for each of the image in these pair, predicts the depth, so how far away every pixel is from the camera. And we also predict the camera pose transform between the two frames. So the camera pose transform has 6 dimensions. Basically, it has the 3-dimensional rotation and 3-dimensional translation. And the depth is basically of the same height and width as the image. So this is a bit different from the conventional systems that we looked at because here we really predict a dense depth and not just for certain feature points that we find interesting. There's really a lot of work also for learning these kind of sparse features, but here we'll stay within the dense depth prediction domain. With a predicted depth and a predicted transform between two images, we can actually take an RGB image, project it out into 3 dimensions, so make a point cloud out of one single image, move the camera, and then project the image back. And this reprojected image we can compare against the actual image that we have at the expected camera position. And this gives us an unsupervised learning objective. And I'll go into the details of this a little bit. So first, let's talk about this reprojection operation. So we assume a linear camera model, but I'll go into what this means in a second. Just to repeat, this camera pose transform, it can be written as a 4x3 matrix where we have the rotation and the translation. It's a 4x3 matrix, but the underlying space that's represented by this only has 6 dimensions, right? So again, the rotation and the translation. And then if we assume a linear camera model, we assume the projection to be linear. And for this, the camera model is described by the camera intrinsics matrix, which is a 3x3 matrix, but has also only 4 parameters. It's the focal lengths of the camera and the offsets of the principal point. So this is usually a property of the camera itself, and can be obtained by camera calibration, and usually doesn't change when you have when you keep the same camera. Then what we can do for a 2D point PA on the first image is we can basically reproject it to a point on the image plane of image B by essentially multiplying with some combination of the intrinsics and adding our predicted depth and then adding our predicted pose. And this gives us a point that's reprojected to this new image plane. Whereas the original point PA is on the grid, so it's on one of the pixel locations. This reprojected one actually has continuous values, so we need to resample it back to the grid of image B. And this is just done by bilinear interpolation, which can be coded in a way such that it is differentiable. And then the second part of this is, so basically now we looked at how we can take one image and project it onto another image. And now we can look at the loss function. So what's actually the learning signal for these kind of systems? We have our neural network, which predicts or takes its input. It takes an image A and then image B and gives us the predicted depths and the predicted camera pose transform. And then, as described just a second ago, we can compute this reprojection. So we can compute kind of an estimate of image B, which is just done by reprojecting image A. And basically, we can then just define an error between the images. So some photometric error where we compare the actual image B to our reprojection of image B. The same thing can also be done for reprojecting the depth. So we can take the depth from image A and transform it, like reproject it to the image plane of image B, and we get an estimate. And then we can also, we would generally want our reprojected depth to be similar to the estimated depth for the same frame. So here again, there's no comparison to an actual depth map because the depth map itself is also estimated by the neural network. So it's really more like a cycle consistency term than it is a real loss function. And both of these kind of losses, so the photometric loss and the consistency loss, can be computed in both directions. So where we can predict the pose from A to B, we can basically also just obtain the inverse pose just by inverting this matrix and compute these same reprojection errors into the other direction. And this is basically all we need to formulate this kind of unsupervised 3D mapping systems. So in my opinion, this is kind of remarkable because these reprojections are kind of natural and pretty simple. And this means that all we need to have really to get both depth estimates and estimates for how the camera moves between frames is really a large collection of overlapping frames. For example, just by a large collection of videos that can be collected. And we don't need any ground truth for either the depth or how the camera moves to train these kind of systems. And So kind of one of the earlier methods that did this, just to show an example, kind of looks like this. And you can see it's kind of, it's not it's not very good, but it's been improved quite a bit. So kind of the depth has been made a lot sharper with some more regularization terms, some better architectures, and so on. And now that we have a system that has the depth for every frame and the camera movement for each, like between each two frames, we could basically make a 3D map out of this kind of system by basically going frame by frame, projecting all the pixels out into our 3D point cloud, and then moving the camera with the camera pose transform. And now I'll talk about my own work. So for now, this has kind of been the basics of these unsupervised learning-based 3D mapping techniques. And we have a work that's coming out very soon, but I'm happy to show some preliminary results from this. And the idea is this kind of explicit inner loop optimization for these methods. And the underlying motivation is one that kind of there's still a lot of room left for improvement. Usually, these kind of conventional mapping techniques that I showed very in the beginning with these feature matching and so on, usually in the end, they obtain a much higher absolute accuracy for the pose and the depth estimates than these learning-based techniques. And this is a little bit to be expected because it's really not a solvable problem, or it's kind of an underdefined problem to estimate the depth from just a single frame and a single prediction. So kind of one example is here where we have this car or a seemingly tiny car with a big coin, but in reality, we just have a really big coin on this car. And it's a problem that appears over and over again. If we just look at a single frame without its context, or even a single object without its context, it's really hard to actually predict the true depth and the true size of the objects that we're looking at. So we really need to look at a bit of a broader context. And just to repeat one more time, so kind of the way that the setup that I've been describing until now is basically we put in a pair of images, we estimate the depth and the poses, and for the 3D mapping, we would just put these into our 3D point cloud. But the actual depth prediction from one image is a bit underspecified. And so the idea for this explicit inner loop optimization for 3D mapping is that we add a inner loop. So I've spoken about this reprojection error, and I've spoken about how we can kind of average it over the entire image to formulate a loss signal. But there's a bit more nuance to the whole story, of course. Basically, the reprojection error is not a scalar, right? So it's just, it gives you a loss on the entire image. And this loss is actually super informative for where our where our depth and pose estimates are wrong. And the idea is to feed this reprojection error, which is has the same height and width as the actual images, back into some sort of inner loop to explicitly update the depth and pose estimation, and then keep refining this at the accuracy that we can either computationally afford or the accuracy that we want, to then hopefully further minimize this reprojection error. And there's two ways that we looked at that I'd like to highlight. So we'll start again with our initial learning-based structure for motion system, which as a single prediction predicts the depth and the pose. And the easiest way to do it is basically to add a second neural network that then optimizes the residual. So basically, we add a whole set of a second neural network that takes the images and the reprojection errors as an input, and then predicts a better depth, hopefully, and a better camera pose transform. And then minimizes again the reprojection error. And this second neural network, so this inner neural network, we call it the unrolled neural network because of some links to MRI imaging that I'm happy to talk about later, but I think for this talk they're a bit detrimental. This component here can be repeated as many times as we want, because after this step, we'll again get a new error map, which we can again feed into this block. The bottleneck becomes a little bit how many iterations we can afford to train. So, of course, for every inner iteration, we need to keep another another copy of our gradients in the GPU at each time. So usually if we can train this kind of initial system, I don't know, with a batch size of 10, then adding one inner loop already halves the batch size, and we keep going. So there's a limit to how much depth we can train. But then at test time, when you want to predict, we can actually just run this as a loop because there's no gradient accumulations. We can run this for as long as we would like. So this is the first way to kind of introduce this explicit inner loop in these 3D mapping systems. And the second one is, maybe it's even simpler actually. So the second one is basically just test time fitting. So we have our learning-based structure from motion system, the normal one, which has been trained on a big data set of image pairs and has the depth and pose estimation as a single step prediction. And now at test time, we again have a pair of images that we want to find a good depth and pose for. And basically the idea is to just run gradient descent on this single pair of images. And so it's really it's a bit more tricky to justify this to the true machine learner who says there's a clear train and test separation. And of course, one could argue that this kind of leaks some information of the tests. Like it's not really a fair comparison in many ways, but in 3D mapping, it's not really this kind of very clear machine learning problem where we have the train and the test. In the end, what we really care about is just having good depths and good pose transforms. And it's also not like we are training on the test set. So we're actually only training the system on the train set. But then at test time, we keep fitting our neural network on a single data point. It's a very rare case, I think, of a problem where this kind of unsupervised learning objective is actually the task at hand. So a lot of times these unsupervised learning techniques are just used to find a good set of weights to initialize some neural network. But here, really, the unsupervised objective actually solves our task of 3D mapping. And the second part is also, there's very rare that unsupervised learning objectives which work in practice can be optimized on a single sample. So when we have these kind of contrastive losses, which are used a lot in unsupervised pre-training, usually we need a very large batch size of many different samples which are compared to each other. But here the unsupervised learning objective is really one sample, and we can fine-tune a neural network with millions of parameters on a single data point, which is kind of rare, I would say. And now we'll go into some results of these two methods. And so here on the x-axis, you have the number of inner iterations. So how many inner steps are we doing? And on the y-axis, you have this reprojection error. And we can basically train, as I said before, this unrolled approach that has a second neural network. We can train this with, I think, 3 inner iterations on the GPU that we had. But we can run it for much longer. So when you run 100 inner iterations, we can see that kind of for maybe up until 6, 7 inner iterations, the self-supervised loss keeps decreasing for the unrolled approach. And then the self-supervised learning objective actually goes up a little bit and saturates at some value, but it's still better than the initial value. So the initial value is basically adding no inner loop, just having this classic single step prediction for the depth and the pose. For the test time fitting approach, you can see that we kind of we get a much better self-supervised learning loss. And if we add more inner iterations, we keep minimizing this loss. So far, this is not very surprising because we're really fitting a giant model onto a single sample. So we would expect that we can minimize this loss. But the question is whether we actually get a good, like better depth and pose estimates from this, even though we keep fitting. One more aspect of this is, of course, the time that it takes to run these inner iterations. So in any case, we're kind of leaving the real-time realm a little bit as soon as we add more inner steps. But we can see that 100 steps of this unrolled approach is much faster than doing 100 steps of this kind of test time fitting approach, because we don't need to compute any gradients. We just iteratively keep running this inner neural network in forward mode. Whereas this test time fitting approach, you need to compute gradient steps every time. So it takes quite long to run this until convergence. If you have a large data set of images, it's not really feasible. But what's interesting is if we actually look at not the self-supervised learning loss, but the actual poses that come out of it, and we compare them to some ground truth poses. So this is for the Kitty autonomous driving data set. We can see that even after like 5 to 10 iterations, we can almost cut the actual ground truth pose error down by 70% very quickly with this unrolled approach, which then saturates like it does also in the self-supervised learning loss. But what's also interesting is that for the test time fitting approach, we don't seem to get any sort of overfitting behavior. So again, we're fine-tuning a big neural network that's been trained on lots of data on a single sample. And even as we keep fine-tuning and adding more iterations, we don't seem to get degenerate solutions, but actually the poses that we recover keep improving. So yeah, in my opinion, this is kind of surprising. There's some links to what's called the deep image prior in signal processing for this test time fitting approach. But in general, I think both of these methods are kind of nice or could be very interesting when you don't really care so much about the real-time behavior, but you want to explore this trade-off between allocated computational time and the accuracy of your structure for motion system. So this is something that will come out very soon of our lab, but I'm also happy to answer any more questions about precise things for this inner loop optimization project. Of course, it has some limitations. So here's an example. This is also from the Kitty dataset. We're driving on a road with our vehicle that's mapping the environment, and we have 2 cars ahead of us, and just eyeballing them makes me say they're like roughly the same distance from the camera, plus minus like a tiny bit, maybe 2-3 meters. But when we optimize this self-supervised learning objective a lot, we get this kind of behavior. So the car that's driving away from us, actually, or driving at the same speed as us, appears very, very far in the distance, whereas the car that's coming at us appears a lot closer. And this is basically just because of how these objects move, right? So if we look at the reprojection, if we minimize the reprojection for an object that's moving away, then the solution is just to move it further away, whereas objects that are moving towards us, the depth that minimizes the reprojection is again moving it closer to us. So we have a limitation when we have these moving objects that kind of move with or against the camera. We get similar sorts of weird behaviors when we kind of when we have other surfaces like reflecting surfaces or see-through surfaces like windows and mirroring kind of behaviors. But in general, we still get much better camera tracking than with single-step approaches. Now, towards the last part of this talk, I'd like to talk about the applied side, the environmental side of my PhD topic. which is kind of using these techniques to map the coral reefs of the Red Sea. And for this, we're part of the Transnational Red Sea Center at EPFL. So this is hosted by one of the, not the ECO lab, but the other lab at EPFL that I'm at, the Laboratory for Biological Geochemistry. And the goal is to cooperate with the local entities of the Red Sea, so scientists, NGOs, and governments of the nations in the Red Sea for coral reef science. And part of this is also bringing new tools from technology to coral reef science, and to establish a baseline of coral reef monitoring in the area. There's a very interesting thing about the Red Sea, which is that in general, the coral reefs worldwide are in decline. They're threatened by warming oceans, and they're threatened by the heat so much because it leads to these mass bleaching events. However, it's been found that in the Red Sea, the corals tend to be very resistant against heat stress. So as we have climate change increasing to threaten reefs worldwide, the corals of the Red Sea, especially the corals in the northern Red Sea, will probably stay resistant to more degrees of ocean warming than we're probably going to have. So it might be one of the last healthy coral reefs, or the last coral reefs that will remain unchanged by climate change. However, in general, in coral reef science, the monitoring is very work intensive. So the way you would usually, in the conventional way, kind of describe the composition of a reef is to put down a transect line, have these photo quadrats, take these photos and then analyze them after, and then extrapolate from this small area to the entire reef area to determine what kind of corals are there and how many of them are healthy and how many of them are damaged or dead. Or you could use kind of conventional photogrammetry, but for this you really need very controlled conditions. So you need an excellent camera. You would want good lighting conditions, either bring your own strobe or you don't want these caustics. You need to make sure that there's enough overlap between the images. And then you really need a big computational budget, and you get these very nice high resolution scans of smaller areas. But we want to use this learning-based mapping technique because it's very robust to the conditions underwater. And ideally, all you would need to do is basically go diving, turn on the camera, and film the reef, and then get characterization of the reef composition using these learning-based 3D mapping techniques. Especially these kind of techniques should work with affordable cameras. So in this context, we work with GoPro cameras, which are among the cheapest cameras that work reliably underwater. This is also because in many nations that border the Red Sea, the research budgets are a bit restricted. But a GoPro camera basically is available in many places. And if we can map with these kind of cameras using these deep learning-based techniques, it's quite a big step in terms of coral reef monitoring in the Red Sea. So I spoke about kind of the cars that lead to these annoying reprojection artifacts. But there's a very easy way to circumvent this if you don't care about collisions. So if you're not in the autonomous driving domain, but in the diving domain, is just to use a semantic segmentation system and basically just remove all the objects that we don't want to be in our 3D map to begin with. So we have other snorkelers and also fish, for example. We can just remove them with a semantic segmentation system. And then use the GoPro cameras for mapping these reefs. And to show an example of how this looks in the end, here's a video from a coral reef also in Jordan, in Aqaba. So on the top left, we have the input RGB video, which is from a GoPro. It's a very low quality. Again, the lighting is very, very bad. The color changes as a function of the distance. The whole thing is a bit shaky. On the top right, we have the predicted depth from our learning-based structure from motion system, which works pretty well when you tune it on enough data. On the bottom left, we have a prototype for a semantic segmentation system. So this will improve quite a lot in the near future. Right now, it's just telling apart like rock, sand, rubble, and then like the main types of corals and whether they're obviously alive or obviously dead, and some fish. But we're working on a larger semantic segmentation data set to cover also more diversity in the Red Sea. And combining these, we can create both a 3D map in RGB space, so we can map the coral reef in this area, but we also kind of for free, if we have this semantic segmentation system, can attach the semantic information to every point in this point cloud and get a characterization of this kind of, or sort of this transect of the reef that we're looking at, and look at the coral cover and other parameters that could be interesting to coral ecologists. And this is, I don't want to brag, but I think in the coral reef science, I think this could have quite some big implications. So I'm really looking forward to also having this be published very soon. So just to summarize the end of this talk, again, conventional structure from motion can be extremely accurate. You can get very, very good 3D reconstructions from sets of images using these established techniques. They're pretty computer expensive if you want them to be very precise, and they also struggle in certain kinds of environments with challenging lighting conditions or dynamic objects. Deep learning-based 3D mapping can tackle these challenging environments, and it's kind of remarkable, in my opinion, that we can frame this as such a nice and simple unsupervised learning problem, but usually they don't reach the same accuracy as conventional systems. However, we can kind of tackle this by introducing these inner loops that optimize this reprojection at test time. We can close the gap a little bit between these learning-based techniques and conventional techniques. This set of methods in general is very, very flexible and it just works out of the box. We can learn to be robust against detrimental challenges by the lighting, for example. And this enables us to use this, for example, for monitoring underwater ecosystems at unprecedented scale. The last thing I would like to say is a big thank you to my collaborators at EPFL. So my two professors, Professor Tuya and Professor Maibam, and Dr. Guillaume Banfandi, who have been very involved in this project as well. Also a big thanks to our collaborators in the Red Sea, so our collaborators from Aqaba in Jordan, from Israel, from Eilat, and from Sudan, and many more. Without them, this work wouldn't have been possible. And now I'm very happy to take any questions.
Thank you, Jonathan. So while waiting for people to come up with questions, I can start asking a couple questions. So you say this there's some issue with this test time fitting because you have some effects on, for example, on moving objects, you said. Is there a way of mitigating that?
I don't think so. As long as you work with reprojections, I don't think it's possible to really fix them. I think you would have to, I mean, there's many approaches to kind of try to mask moving objects in an unsupervised fashion. But in the end, it all comes down to the same thing, which is trying to remove the moving objects instead of including them in the reprojection.
how large are the data sets that you're working with?
That's a very good question. So in terms of the video samples that we got, now it's getting really big. So for the coral reef project, we have now collected approximately 200 hours of GoPro footage from Israel, from Jordan, and from Djibouti. And there will be some data coming in from Sudan very soon also. So the data for training this unsupervised mapping system is really enormous at this point. We're talking about 6 terabytes of video when it's compressed. For the semantic segmentation, we're of course working on a few orders of magnitude that are a bit smaller because of the manual annotation effort. So here we're talking only a few hundred frames for now.
And you're using all that data when you train your depth models. Exactly.
Usually when we work on the more method development side of these things, kind of some of the examples that I showed were from autonomous driving data sets, because there you really have ground truth depth and ground truth post transforms to evaluate against. We usually try to develop the methods on these and then kind of move them to the coral reef domain where we don't have any ground truth.
Don't you have any ground truth to evaluate in the end?
Well, for the coral reefs, it's a bit more difficult, right? So we would have to match this maybe with a depth scanner, for example. So one thing that we do is we work on these transects for testing purposes. So this is a straight line that we literally place on the floor. And then we would want if we go back and forth over the multiple area, we would want the point clouds to align precisely. So if you go back and forth on a transect, we want to make sure that the camera ends at the same spot that we started in. But it's not as precise as a true error metric as maybe in autonomous driving, where you really have a ground truth for every single camera movement.
Great, interesting.
Thank you.
Some more questions. We have a question from Eric.
Yes, thank you very much, Jonathan, for your presentation. So I have a question regarding relationships to neural radiance fields. So this has been used lately for example, 3D reconstruction. Are there a relationship, and how do they compare with the method you presented?
So this is a very excellent question. So neural radiance fields are like a very hot topic, of course, in computer vision, because they very nicely deal with also these non-Lambert surfaces. So if we have the water, for example, which is not see-through, then in a neural radiance field, maybe I think I even have a slide somewhere on them. Then we have this differentiable rendering, and we could really nicely model the water in between. The problem with neural radiance fields, from my understanding until now, is 2 things. They take very long to train, and they're usually bounded to a specific area. So usually you have your neural representation of the scene, which can capture very nice renderings of the camera moving around within the scene. But if then we move further away and further away, at some point we kind of run out of capacity to render this kind of field. One more thing is that at least with the kind of videos that we work with, which are very noisy and again, kind of very, in terms of challenging lighting conditions, it's already kind of challenging to even match the camera perspectives, which is a prerequisite for fitting nerves. There are some extensions of the nerve framework which look at also like fitting the camera angles at the same time as fitting the nerve. And they seem to work, they seem to end up very precisely. But the training times are really long. As far as I know, for these kind of natural videos that we also look at, we're talking about something like 40 hours of fitting on a powerful GPU for like 2-3 minutes of video. And you get a very, very nice rendering in the end and a very accurate 3D representation. But for now, these speeds are not practical for monitoring things at scale, where you just take the camera, go, and just basically with a simple like ResNet 18 unit, you can run it on a laptop and you can get the 3D maps out. But it's a very good question. Thanks.
Great answer. Thank you.
Hi, thanks for a very interesting presentation. I was wondering, the method that you have talked about, this unsupervised method, does it generalize well between different types of video domains? You mentioned these self-driving car videos versus underwater videos, for example. Like, have you done any such assessments or know anything about that?
That's also a good question. It seems that in computer vision, there's a lot of benchmark data sets from the autonomous driving domain, and usually this kind of domain transfer is evaluated from one autonomous driving data to the other. So I don't know, we have some self-driving car or some car in Karlsruhe in Germany and another one in the States. And then this is often portrayed as a domain shift. There's a lot of very interesting work on things like nighttime driving or driving when it's snowing or raining or foggy. So these are the domain shifts that researchers are looking at a lot in this computer vision domain. I have to admit that I'm not really on top of this literature right now. I think it's a valid question, and I'm really hoping that in the future we really get to look at bigger domain shifts also, that we get maybe some sort of benchmark suite which has very diverse data sets, not just different flavors of autonomous driving, which allows to quantify this generalization more precisely. I also think that maybe within the near future, we'll see something like foundation models for this kind of prediction. So something that instead of trying to adapt to the individual domains, that's just trained on such a large data set of videos from different domains that it'll actually just generalize to all kinds of video domains. But I would expect this to come out of maybe a industrial research center. But it's a very good question, and I wish I knew a better answer.
Thanks, that's a great answer. And speaking of generalization, you talked about this fitting to a single test sample, so to say. I suppose those models were first pre-trained on some large training set, and then, so I was wondering, have you maybe tried to just fit from scratch to a single example, and also just in general trying to vary the size of the first training set when generalizing to that single point in fine-tuning?
The answer is we have not, but this is actually what I've been thinking about quite a lot recently. So I don't know if you're familiar a bit with the inverse problems literature. So there's a thing called the deep image prior, which basically does exactly this. So you fit an entire neural network from scratch on a problem that you're trying to solve. And you realize that for a lot of image processing problems, there's a lot of structure already encoded into the structure of the neural networks that allows solving tasks on a single sample, like by fitting on a single sample from scratch. I tried a little bit to fit a neural network onto the single sample, and I couldn't make it work. This doesn't mean that it doesn't work in general. This could mean that I wasn't patient enough, that there's some regularization terms that should be devised. There's also, when you have these kind of things, you usually get very detrimental effects from batch norm, as always. But this would be very interesting to actually look at in depth to see how much this actually matters. How much does it matter that we need to pre-train on a large data set before we can test time fit? And of course, you need to also run an order of magnitude or 2 or 3 order more of iterations, right? So this won't be fit with 50 iterations. There you would more need like 5,000 or 50,000 iterations, like in the deep image prior. But yeah, thanks for the question.
Makes sense.
Any other questions?
Well, I have one more. So I was wondering, you mentioned the 2 approaches, the unrolled approach, and then you talked about this fitting to a single point approach. Are they combinable or something like that? Both of those, or are they like mutually exclusive or something like that?
In my opinion, there's no reason why they shouldn't be combinable. It's something that we haven't extensively evaluated. So there's it becomes a bit of a heuristic kind of thing, right? So for example, you can devise all kinds of interesting combinations of the two, where maybe you do one step of unrolling, one step of test time fitting, and you keep iterating. So you really open up kind of a Pandora's box of combinatorial problems and heuristic problems. But I would expect it to work, but the truth is, I don't have any good data to show you for this.
Yeah, I understand fully. Thanks.
Do we have a final question for Jonathan? Otherwise, thank you very much, Jonathan, for this great talk with some really interesting results. Next week is Ascension Day on Thursday, the May 18th. So we'll be back in 2 weeks' time, May 25th, with Puchao Chang from KTH, Royal Institute of Technology. It's going to talk about multi-source satellite remote sensing for large-scale wildfire burned area mapping using deep learning. So welcome back in 2 weeks' time.
So thanks everyone from my side. Also, thanks for being here. Thanks for the great questions. And thanks again to the organizer. It was a pleasure.